Hey guys, Mr. Bowman here. We're looking at 2.12 probability methods in this video, and we're going to focus on all the excellence questions from the 2016 exam. So from the website in the description below, I've got a link, and question number 11 was the first from that exam, and we're carrying on with that apple theme that's been pretty common in all the questions. So for the records, we've been showed during the first harvest, 70% of apples are picked. In the second harvest, 35% of the remaining apples are picked. We've been given some more information about where the apples go this time. We've been told 9% of apples go for export, 31% go to the local market, and the rest are sent to the factory to be made to apple sauce. The question asks us if an apple is being sold on the local market, so we only care about the apples who are sold to the local market, what was the probability that that apple was from the first harvest? So before we start this question, earlier on, we would have done a probability tree from this scenario. And the first branch relates to the first harvest. I'll call it the first 8. And an apple can be picked or not picked at that harvest. From the question, it had a 70% or a 0.7 chance of being picked, which means it had a 0.3 chance of not being picked. When the apple was picked, it was then sent to its destination, either export, the local market, or the factory. So let's split that off. So I'm going to go for E for export, I'm going to go for LM for the local market, or the F for the factory. It was 9% or 0.09 for export, it was 31% or 0.31 to the local market, and the rest, which will be 0.6, was sent to the factory. We've now got to look, if the apple maybe wasn't picked, so it's still sitting on the tree, there's going to be a second harvest. And at that harvest, there was a 35% chance of those apples being picked. So from here, we're going to have another split. It's going to be picked or not picked. That there is 0.35, which means the bottom there must be 0.65. If the apple isn't picked, that means the apple doesn't get used. It just kind of sits there. Maybe it falls to the ground and biodegrades. But the apples that were picked on the second harvest over here, they are also then going to be sent on to their destinations. So it could go to export, it could go to the local markets, and again, it could go to the factories. And the same percentages apply, 0.09, 0.31, and 0.6. So that was the fairly messy probability tree that you would have had to done, or you needed to do for this particular question. And we're now going to think about what we've been asked to calculate now. So if the apple was from the local market, what's the probability it's from the first harvest? So this question is asking us about finding the probability of the first harvest given they were sent to the local market. And this question, we're going to need to think about F over T to help us with this. And the total relates to all of the apples, or the proportion of all of the apples that were sent to the local markets. And they are ones where the branches end with LM, or the local markets. So that first option would be 0.7 times 0.31. So we're going to put that there, 0.7 times 0.31. And we're going to add the second option, which is 0.3 times 0.35 times 0.31. So we're adding 0.3 times 0.35 times 0.31. So those are both of the ways the apples can be sent to the local markets. And the numerator, of the two options we looked at, we only care about those who went to the first harvest. We need to put that on our denominator, or on our numerator, and that there would be the first local market group, or 0.7 times 0.31. So we've got 0.7 times 0.31. When we put that into the calculator, the numerator is going to be 0.217, and the denominator is going to be 0.24955. And finally, you convert that to your final probability, and that's 0.8686 or 96, and that they had a 4DP rounding. So what this number means is about 87% of the apples that went to the local market, they would have come from the first harvest. So we are now at question number 12, and I've left that blue diagram from question 11 because we're going to need it for this question as well. We've been told if there are 120 apples in an export carton, if 172 export cartons are produced, how many apples win the total crop? So the first thing we needed to do is we needed to find out, well, how many export apples are there in total? And we do that by going 120, which is the number of the number of apples in a carton, times by 172, which is the number or the total number of export apples. And that's going to be 20,640. So we know there's 20,640 apples. And normally when you're dealing with these bigger numbers, you should be thinking expected value. So the expected value of an event is equal to the number of trials times the probability. So we've actually already got the expected value, the number of export apples. The issue is we don't have the number of trials. In fact, that number of trials is actually the total number in the crop. That's what we're trying to calculate. So the only thing left in this equation is the probability. So we need to find, well, what's the probability of an apple being an export apple? That's what we're going to do over here. So we need to find, well, what's the probability of being an export apple? And that's where our tree comes in. The ones ending with E up here and here, these are the two ways an apple can become an export apple. So we're going to add together the two branches which they relate to. That's going to be 0.7 times 0.09, and we're going to add 0.3 times 0.35 times 0.09. Put that into your calculator, you're going to get 0.07245, and that means we've got about a 7% chance of a random apple being sent out for export. Okay, so now that we've got the probability, we're going to substitute the two numbers we know into the equation. So we've got the expected value, or how much we're expecting, and we've got the probability. We can now solve for n. So 20,640 is going to be equal to n times 0.07245. Opposite of multiplication is division, so we're going to divide both sides by that number. And when you put that into your calculator, you're going to get quite a big number, 284,886.1, and that they had a 1 DP rounding. The issue is you can't have 0.1 of an apple, and if we have 0.1 of an apple, we might actually be one apple short for one of these export packages. So what we're going to do is we're going to round that up. So n is approximately 284,887 apples. We are now on to question number 13, unlucky 13. So at a Pepsi Galore orchard, there are two types of apples, Jazz apples and Beauty apples. There are twice as many Jazz apples than Beauty apples grown. Table 1 gives us information about the probabilities being picked. Table 2 gives us probabilities of where the particular types of apples are going to end up. A minimum of 120 export cartons must be of the Beauty variety. Show by calculations to support your answer if this condition can be met from all the scenarios we've got. So what this tells us here is this tells us the probability of a Beauty apple going to export that must be larger than 120 out of 294. So that means the probability of Beauty given export, that number has to be more than 0.4082. And that they had a 4DP rounding. So we're dealing with a bit of an inequality, which is going to make this a bit messier, but that does explain why it's an excellent question. Next step, we're going to use all this information to calculate what that number actually is, and then we're going to make a comparison to see if the condition is met. So the probability that an apple will be a beauty apple given it was an export apple, we do need to think F over T for this particular question. And the numerator down the bottom, that's going to relate to the probability that an apple is going to be exported. So we need to think about jazz apples and we need to think about beauty apples. So we'll start off with jazz apples. So the first thing to note, the probability of a jazz apple is 2 out of 3. And that's because we were told that they were picked for a certain ratio. Right at the very top, twice as many jazz apples as beauty apples. So 2 over 3 is the probability of a jazz apple. We're then going to times that by the probability that a jazz apple was picked, which is 0.85, because it has to be picked for it to go to export. And then it's going to be times by the probability of the jazz apple being sent for export, which is 0.12. So times 0.12, we're going to add the probability of a beauty apple being sent for export, and a beauty apple will be the other 1/3. So notice 1/3, 2/3. Times by the probability of a beauty apple being picked, which is 0.95. And then we're going to multiply that by the probability of a beauty apple going for export, 0.15. Going over there. So we're using a lot of the multiplication theory that we've looked at. So that's all of the apples, or the proportion of apples going to be exported. We're now on the numerator just going to put in the beauty apples because we don't really care about the jazz apples. And if you remember, that second part there applied to the beauty apples, so that's also going to be on the numerator. So that there will be 1/3 times 0.95 times 0.15. So pretty messy F over T type calculation. We're going to simplify that. If you simplify the top, you're going to get 0.0475. That's going to be divided by 0.1155. 0.4113, and that there had a 4 dp rounding. So we now need to compare this number with the number that we have above. And what we can see is the actual probability is greater than the probability that we needed here. That means that condition has been satisfied. So in a little sentence, as 0.4113 is greater than 0.4082, the condition has been met. So pretty messy question, particularly with the F over T type stuff. You might have wanted to use a probability tree there, but that could have been pretty time consuming as well. We are now on to question number 14, more apples related stuff. We've got an apple orchard, and here's a sample with data. And this two-way table looks at if the apples are diseased or not versus if they were conventionally grown or organically grown. It is claimed, so that word claim normally links to a relative risk question, that conventionally grown apples are twice as likely as diseased apples to be diseased apples than organically grown apples. State whether you agree with this claim. So yeah, claim, this is relative risk. So what we need to do is we need to find out the probabilities. So we're looking at conventional apples and organic apples, and we're interested to see if they're diseased or not. So we're going to first have to find out what's the probability that an apple is diseased, given they are conventional. And we're also going to have to find out that what's the probability that an apple is diseased given they are organic. So F over T is how we deal with these questions. Conventional apples relates to the total, and per our graph or our table there is 640 conventional apples. Of these conventionally grown apples, how many of them diseased? We've got 122. We now put that into our graphics calculator, and we're getting a probability of 0.1908, and that there had a 4 dp rounding. We now need to do the same with organic apples. So F over T is where I'm starting. How many organic apples are there in total? 560. And of those 560 apples, how many are diseased? 58. We put that into our calculator, and I'm going to get 0.103. 6. And again, I've stuck to my usual 4DP rounding. Now that we've got the two probabilities, we're going to jump into relative risk. So relative risk, just a reminder, I normally do the big number divided by the small number. That is 0.1906 divided by 0.1036, and I get a relative risk of 1.84, 2DP rounding. So we now need to explain, well, what does this 1.84 actually mean? And once we've explained that, we need to check, is it consistent or different to the claim that's been made? So this tells us that conventionally grown apples or in group, but conventionally grown apples are 1.84 times more likely to be diseased when compared with organic apples. So that's what 1.84 means. At this stage here, you probably got yourself a merit. Reconciling that with the claim made is how you're going to get excellence. So let's look at the claim in a lot of detail before we make a decision. So conventionally grown apples are, it says specifically, at least twice as likely. So what that's saying, it is 2 or more times likely. Our 1.84 is less than 2. That definitely is inconsistent. That is not more than 2. That is less than 2. So based on that, I'm probably going to say this claim is wrong, because 1.84 is not more than 2. So as our relative risk of 1.84 is less than 2, conventionally, oh, there you go. Instead of saying that, I'm just going to say I disagree with the claim made. The claim made. We're now looking at question number 15. So we've got about the jazz and the beauty apples again. Here's some data. And they've given us some more information about the apples. The key thing to note, this here looks at conventionally grown apples and organic apples, and this is diseased or not diseased apples. It is claimed that apples are more likely to be diseased depending on their variety or their type. So this table here doesn't actually have the information we're looking for. So we're looking to compare if they're diseased or not with their type, but this is how they are grown. What we need to do is we need to redo our table for what we've actually been asked to look at. So what I'm going to do is I'm going to write diseased and not diseased, and this time around I'm going to write jazz apples and beauty apples, because they're the two types that we've been asked to investigate. There is still 1,200 apples in total, and I got that from the original table, and I know that 180 apples are diseased, so I'm going to put 180 up here, and I know 1,020 apples are not diseased. That there is going to be 1,020. I'm now going to use the other information from the question. We were told 890 apples are of the jazz type. That there is 890, which means that there is going to be 310. And I'm also told that 182 apples that are beauty are not diseased. So beauty and not diseased, which will be this box here, that's going to be 182. 182. We are now going to fill in and populate the rest. So 310 minus 182 is going to equal the beauty diseased apples, and that's going to be 182. Oh gosh, sorry, that's not right. That's going to be 128. Then there will be 52, which is 180 minus 128. And the final number is going to be 338, which is 890 minus that 52 there. So I've now got a table that actually looks at what I've been asked, whether or not they get diseased versus their type. And again, I can see that word claim. So like the previous question, claim coming up again, And we've even been told about absolute and relative risks. But like the previous question, it's a relative risk question. So there was 2 excellence questions that were relative risk here. And the first thing we need to do is we need to consider the types of apples, Jazz and Beauty, and whether or not they're diseased. So we're going to go, what's the probability that an apple is diseased, given that they are a Jazz apple? And then we need to move on, well, what's the probability that they were diseased, given that they were a Beauty apple? So let's go ahead and calculate both of those numbers. We need F over T to do both of them. The first one, the Jazz apples total, relates to the number of Jazz apples. Just a reminder, we only care about the Jazz apples here, and that's going to be 890. And of those Jazz apples, how many of them diseased? We got the 52 up the top there. We then plug that into our calculator. We're getting 0.0584 to a 4 dp rounding. We now need to do the same for the Beauty apples, so we only care about the Beauty apples for this calculation, and there's 310 of them. And of those 310, how many are diseased? And we've got 128 of them. So that's quite a big proportion actually, isn't it? When we plug that in to find a probability, we're going to get 0.4128, and that they had a 4 dp rounding. So straight away we know these numbers are hugely different to each other. So the type of apple, being a Jazz apple or a Beauty apple, is definitely going to make a big difference. So let's find the relative risk, just to confirm that. Relative risk. And we know that that's going to be the big number, which is 0.4129, divided by the small number, 0.5589. And I'm going to get 7.07 with a 2 dp rounding. So what that tells us is these Beauty apples are actually 7 times more likely to catch diseases than the Jazz apples. So let's explain that. So this tells us that Beauty apples are 7.07 times more likely to be diseased than Jazz apples. So that's a huge difference. Definitely going to buy Jazz apples instead of Beauty apples. Now that we've made that, we now need just to reconcile that with the claim that was made. And the claim said certain types of apples are going to impact on, whether or not they're diseased or not. And there's really clear, slam dunk, that that's the case. Based on this, just going to summarize this. Based on this, the apple type, I've written apply, apple type makes a big difference So it makes a big difference on whether it will get diseased. I've written is will. So whether it will get diseased. There we go. Second relative risk question, really important one. Now let's move into question 16, the final one. So question 16, just realised there's actually a question 17 from this exam because they had an extra excellence question for some reason. But what we've got is we've got apples sent to the factory to made sauce and then they are bottled. Just noting, I've got some probabilities from the previous questions. Testing is showing when the bottling machine is operating correctly, the weight of sauce dispensed into bottles can be normally distributed. So that's nice to see that it's a normal distribution. There's the mean and there's the standard deviation. The quality control process of the random 3 consecutive bottles, if more than one of these bottles is found to be over or underweight, then the machine is going to be checked. So what that means is they're picking 3 bottles in total, and if 2 or 3 of them are classified as overweight or underweight based on the probabilities above, then that machine is going to be checked. If it's 0 or 1 bottle, then they're like, oh, well, the machine's probably going okay, and they're not going to check it. After the random sample is taken, what is the probability that the machine needs to be checked? So the first thing we need to do is we need to find out, well, if we're talking about 1 bottle, just 1, what's the probability that that bottle is, it's going to be over or underweight? And this is really important because these are the bottles that need to be checked, or they're the ones that are going to trigger the check if there's enough of them. And that probability is going to be the two probabilities given to us added together. So 0.01313 plus 0.05, that's going to get me to 0.06313. So that's the probability a bottle will be over or underweight. We also need to think, well, what's the probability it's not going to be over or underweight? So not over or underweight. That there's going to be 1 minus that above probability. So it's going to be all of the other bottles. And when you put that into your calculator, you're going to get 0.93687. And it's going to get a bit messy here, and there's a few options to figure out the 2 out of 3 part. You can draw a probability tree, which will be a bit messy, or you could think of all the combinations that would require this to be checked. So if you think of bottles, bottle number 1, bottle number 2, and bottle number 3. So let's say a tick means it is okay, and a cross means there's some kind of issue, it being over or underweight. So the first thing to note is if all of them are crosses, cross, 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 that machine is going to need to be checked. If maybe the first and second bottle, maybe the first bottle is okay and the next 2 are not okay, that will need to be checked. Maybe the first one's bad, but the second one's okay, and this one's bad, that needs to be checked. And finally, maybe it's bad, bad, and checked, and that's okay as well. So these 4 combinations are the only 4 combinations that would have resulted in 2 or 3 bottles being over or underweight, and then the machine needing to be checked. So we need to calculate the probability of all of these separately. And luckily there's going to be some commonalities. So these 3 here are all 2 ticks and 1 crosses, which means we need to find the probability of one of these, and then we're just going to go times 3. But the probability that the machine needs to be checked is going to be equal to the probability of XXX, and those are weird, but it refers to the crosses over here, plus 3 times the probability of tick XX. And you could have picked any of the 3 combinations there because they're going to be the same. So we now need to figure out, well, what's the probability of XXX? And that there would be this number here times itself twice. So 3 times actually. So this is the first bottle, 0.03613. The second bottle is the same. So we're using the multiplication rules here, 313, and then we're going to times it yet again. So that was the probability of the first bottle being over or underweight, the second bottle, and the third bottle. Once we've done that, we're then going to add 3 times the first tick is it not being overweight or underweight. So that's that big probability there, 0.93687. We're then going to multiply it by the other 2 bottles, which should be over or underweight. 0.0613, or getting that wrong, there we go, 313 times 0.06313. So that there represents the 4 different combinations. The first one is 3 crosses, or the 3 over or underweight bottles, and the second one is the 3 different combinations where there can be 2 over or underweight bottles. Put that into your calculator, and you're going to get 0.1145, and that there had a 4dp rounding. So probably not going to need to check the machine, but there's about an 11-12% chance that you will need to. We're now up to question number 17, and basically we've been given a normal distribution model in figure 1, and then they have taken a sample of 150 bottles. These are the full source bottles, and this is the distribution of that sample that they took. We've been asked to compare the probability distributions with the frequency histogram. And in our answer, we should compare the shape, the center, the spread for both distributions, and we should provide numeric evidence. So what this is trying to get us to do is, hopefully you recall from inferences, you're doing a bit of a CSSI plus a probability calculation at the end. So notice I put them in a different order. The order that you approach them doesn't really matter, but I always tend to start with the center. So for center, and then I'll probably just jump into figure 1. So for figure 1, we've got a normal distribution, and in that case, the mean, the median, and the mode are all about the same. And in the middle, that's probably going to be about 310 grams. So I'm just going to write for figure 1, the mean, median, and mode. Weight of applesauce in the bottles. Are all around 310 grams. So key thing is I've got that number because it specifically did say to provide numeric evidence. We're now going to move on to, well, how does that contrast or compare to figure 2? And the first thing I'm noticing is there definitely is a right tail. And when there's a right tail, so the mean's normally in the middle, and a right tail normally stretches the mean and moves it to the right. But we can also see that one big group there in the middle, that's probably going to contain the median and the mode. So we know that the mode and the median is going to be between 302 and 304. And because of that skew, that right skew, we know that the mean is going to be bigger or more than those. And that's different to above, where they're all about the same. So this should be contrasted. So forgive the messy handwriting, just lots to write here, and the poor spelling. This should be contrasted with our sample. Which should have a mode and median, which should a mode and median between 302 grams and 304 grams. However, and then I'm now going to talk about that right tail or that right skew. The right skew suggests that the mean will be slightly higher. Than these. And then, so we've got our numeric evidence. We do need to make a comparative statement. How does that compare to the above? The key thing to note is, because 310 grams is up there, all of these averages are below the averages from figure 1. All of these averages, I'll put averages in quote marks, are less than the center of figure 1. So that's an interesting thing. So this sample contains a lot of apple bottles that were on the lighter side, and one that was in the top half. Okay, I'm not sure what happened then, but let's move on. Now that we've done the center, we're now going to have a look at the shape. And we have done a little bit of that. That helped our center discussion with the right skew. There we go. So we've now got the shape, and again, we're going to start off with figure 1. Figure 1 really is that classic normal distribution bell shape. So this is a bell shape. Which is the classic normal distribution. And we should probably go into features about there being one peak, it being symmetrical, and the tails being identical. So this graph, oh sorry, I shouldn't use the word graph, it's a distribution. This distribution has one peak at 310 grams, again using numeric evidence. It is symmetrical. Forgive the bad spelling there. And 2 tails which are unlikely to occur. There you go. So that's a pretty slam dunk in terms of its shape. Definitely a normal distribution. And then now shifting on to figure number 2. This does have elements of a normal distribution curve. It's got a peak in the middle and it goes down either side, just like a normal distribution curve. However, the key feature here definitely is that right tail or that right skew. So this distribution is right skewed. You'll then probably talk about the tails. So the left tail sits between 298 and 202. The left tail sits between 298 grams and 202 grams. Oh, sorry, 302 grams. And the right tail sits between, don't know these numbers, let's have a look at our graph. So what's that, 304 to 212? Between 304 grams to 312 grams. So yeah, so that really supports that right skew that we're talking about, and I've also got some evidence. We could probably mention that it has one peak. It also has one peak between 302 and 304 grams. There we go. So that finishes up the shape section. What I'm going to do is I'm going to clear our center discussion so we can get into the spread. So we're now on to the spread part. And when you're dealing with the spread, we're normally going to talk about the range of each shape, each distribution. So we've got figure 1 up here, and we can see it starts at 296 over here and goes up to 324. So this has a minimum of 296 grams and a maximum of 324 grams. This results in a range of 28 grams. So that's figure 2. Pretty short one there because we've got nothing to contrast it with, but we'll do that when we look at figure 2. We go figure number 2. We can see it starts at 298 and it goes up to 312. So same thing again. Let's talk about the minimum, the maximum, and then the resulting range. This has a minimum of 298 grams and a maximum of 312 grams. This results in a range of 14 grams. And I guess the key thing to note is when you've taken a sample from a population, so when we've taken a sample from here to here, we should expect, a few from here, but most of the data out from the middle there. That's not really reflective in that. We're missing quite a bit of data in our sample. We now just need to mention how different. So this is really, really different. So the spread for figure 2 is much smaller than figure 1. So these are kind of contrasting or comparative statements. So I'm now going to get rid of our shape discussion just for us to wrap up our analysis with a probability calculation. So we're now dealing with some kind of probability references. And we're going to start off with by figure 1. And normally what I do for these is I'll look at kind of the middle of the data for the normal distribution. So we would expect 50% to be 310 grams or more. So that means the probability that X being the weight being more than 310, that's going to be equal to 0.5. I'm then going to have a look at figure 2. And I'm going to be basing it on the number from there, not necessarily the middle of this particular group. And what we can see is above 310, there's probably only, maybe 2 or 3 apple bottles that are above that weight. And that's, don't forget, out of a sample of 150. So let's say there were 3. So there are 3 out of 150 apple sauce bottles that are above 310 grams. So if you think of that as a probability, F over T, that's going to be 3 over 150, and that there is 0.02. So that's a huge difference. Like, that makes absolutely no sense. That's really interesting and really maybe wrong. I'm not sure. So probably need some comparative statement. So the probability, or the probabilities, are hugely different. It appears most of our sample are lighter. I'll go back to lighter. So are lighter apple sauce bottles. Sauce bottles. This is actually so different. I'll suggest they take another sample just to check. Take another sample. Which should be more representative. There we go. So, fairly long video. That wraps up all of the excellence questions from that 2016 exam. Hopefully you found this video useful. Thanks so much for watching.